Dr. Jimmy bringing you mathematics and medicine and the life sciences. In this installment, some of the very basic models for parts of the blood circulation in the human body. We have to worry about those blood vessels, some big, some small, capillaries, big arteries and veins. And then, in there somewhere, we have a beating heart. So, let's begin. We look at a little chunk of a blood vessel. We have flow going in, Q1, and flow going out, Q2. But in a steady state, where we haven't stabbed somebody and we have blood rushing out of the system, in and out flows in a little piece of a vessel should be the same. So we'll just use a Q. So what happens? We have pressure at one end and pressure at the other, P1 and P2, and a volume in the middle. So, two types of vessels. The very little ones out in the tissue, where we get molecular exchange with the tissues, those vessels are pretty much always the same size and present a resistant vessel. So they resist the flow going through. So we have a difference in pressure from one end to the other. So our flow is the pressure difference divided by some resistance factor for that particular vessel. And then we have compliance vessels. Those that expand and contract with the flow, or might be muscular with that ability. So the pressure going in and the pressure going out is the same because the vessel can expand to absorb. So the volume is proportional to the pressure. V equals Cp. C being a compliance factor for that particular vessel. Dr. Jimmy, what's all this compliance? I don't understand. What can you tell me some more? Well, let's see. We have those compliance vessels. So they can contract or expand to absorb the pressure. So something like, let's take this rubber glove. Okay. See the pressure? It equalizes. So the pressure on my end and the pressure on your end is about the same. So that's like the bigger arteries, the heart, and some of the smaller arteries and veins, but not the capillaries, because this one can expand and contract to take care of the pressure. And then we have the resistance vessels. So here's a little pipe, but I stuffed some paper towel in there to give the idea of the resistance. So now, if I put some air in one end, it comes out the other, but not near with the pressure it goes in. See? Lots of pressure on one end, not so much on the other. Those are like the capillaries. Ooh, cool, dude. Okay. Now, what else is in this system? Well, we also need the heart, the pumps. So basically, those are compliance vessels. V equals Cp, but now everything depends on time. The compliance factor changes over time, where for the other vessels, it doesn't. It's a constant factor. So, what are we going to do? Well, right now we want to worry about something that has to do with the pump that's not so time dependent. So let's look at the pump at diastole. So we have this full volume of the heart blood is some compliance at diastole, and the pressure on the venous side with the valve closed, so the arterial pressure doesn't come into play yet. So turn that into cardiac output. So Q, the flow, the cardiac output is the frequency, the heartbeat, times the stroke volume. So that all breaks down, so we get Q equal K times the pressure, the venous pressure, K being the pump coefficient. Ooh, kind of cool, dude. Let's see. Got any more in there, Dr. Jimmy? Oh, I suppose. We can put it all together. So, we have two pumps, a left and a right. We have blood flowing on the pulmonary side, through the lungs and back to the heart. And on the systemic side, through the body and the tissues and back to the heart. If we take all of these pieces, it's all going to come together. Certain parts being compliant, V equals CP, certain parts being pumps, Q equal KP, and certain parts being resistance down in the capillaries, whether on the pulmonary in the lungs or in the body tissues. We have RQ is equal to the difference in the pressures from across venous and arterial pressures. Oh, that's kind of cool. Let's get going. Okay, and next time we'll see how we can put that together and eventually add a little time. So at the moment we have more of a heart pump that's going to look like something that's constant instead of pumping. So, but we need a basic model first. Ooh. Hey, Susie, you want to meet at the jail later? Okay. See you on another day with another installment.